There's something truly remarkable about watching raw iron ore transform into the steel that built America's skyline. At Salzgitter Flat Steel in Germany, they've perfected a process that would have made our grandparents' jaws drop. The journey begins in their towering blast furnace, where iron ore, coke, and limestone meet temperatures exceeding 900 degrees Fahrenheit. Think about that for a moment. That's hotter than lava. The molten iron flows like a river of liquid fire into massive ladles, each holding up to 300 tons. Now, back in the day, steel mills were dirty, dangerous places, but Salzgitter's modern facility uses advanced filtration systems that capture 99.9% of emissions. Next comes the basic oxygen furnace, where pure oxygen blasts through the molten iron at supersonic speeds, burning away impurities in just 20 minutes. The precision here is astounding. They're controlling chemistry down to parts per million. This isn't your grandfather's foundry anymore. The continuous casting process is where the magic really happens. Molten steel pours into water-cooled copper molds, solidifying into slabs up to 12 inches thick while still moving. It's like watching taffy being pulled, except it's 3,000-degree steel moving at 20 feet per minute. These slabs then travel through a series of rolling mills, massive machines with rollers weighing hundreds of tons, that squeeze and stretch the steel thinner and thinner, sometimes reducing thickness by 90%. The final product? Steel sheets so precise they're measured in thousandths of an inch, ready to become everything from automotive bodies to appliances that'll last generations. This is the WinGDRT Flex 96C, a two-stroke, low-speed marine diesel engine that holds the title of the most powerful diesel engine ever built. Standing nearly 14 meters tall and weighing over 300 tons, this beast produces a jaw-dropping 108 920 horsepower. That's roughly the same as strapping 1,000 pickup trucks together. Each of its 14 cylinders has a bore of 960 millimeters, wide enough for a grown man to stand inside. Engineers use precision overhead cranes, laser alignment tools, and hydraulic torque wrenches to fit every component to within microns of tolerance. It's not just an engine, it's a floating power plant, and watching it come together is one of the most awe-inspiring things in modern engineering. Industrial boilers are the unsung workhorses of modern civilization. They power chemical plants, refineries, paper mills, food processing facilities, and even hospitals. These aren't your basement water heaters. We're talking about pressure vessels that can hold thousands of gallons of water and generate steam at temperatures exceeding 600 degrees Fahrenheit at pressures of up to 3,000 psi. Getting that right means there is absolutely zero room for error. The process starts long before any steel is cut. Engineers begin with detailed design specifications, factoring in the required steam output, fuel type, operating pressure, and the environmental conditions the boiler will face. Once designs are approved, the first major step is steel plate preparation. Heavy-gauge carbon steel or alloy steel plates, often 1 to 3 inches thick, are carefully inspected for surface flaws, then cut using plasma or laser cutting machines to precise dimensions. These plates will eventually form the boiler's shell, drums, and headers. Next comes one of the most critical steps, rolling and forming. The flat steel plates are fed through massive plate rolling machines that gradually bend them into cylindrical shapes. This requires enormous pressure, sometimes hundreds of tons, applied slowly and evenly to avoid cracking or warping the metal. Skilled operators monitor the curvature continuously, measuring against templates to ensure a perfect round shape. Then comes welding, and this is where the craftsmanship truly shows. Industrial boiler welding is no ordinary job. Every single weld must meet ASME boiler and pressure vessel code standards, which are among the strictest in any industry. Welders certified specifically for pressure vessel work use submerged arc welding and TIG welding techniques to lay down deep, consistent, defect-free beads. Tube installation comes next. Hundreds, sometimes thousands, of boiler tubes, typically made from seamless steel, are inserted through tube sheets and expanded or welded into place. These tubes are the pathways through which water is heated into steam. Proper tube-to-sheet sealing is critical. Any leak here could be catastrophic under operating pressure. The completed boiler assembly then goes through a hydrostatic pressure test, filled with water and pressurized to 1.5 times its rated operating pressure. Engineers monitor every inch of every weld and fitting for any sign of seepage or deformation. Only after passing this test does the boiler earn its certification plate. Finally, insulation jacketing, control instrumentation, safety valves, and burner systems are installed before the unit is prepared for shipment. Welcome to the world of hard turning and lead-free turning, as performed on the legendary VDFT and VDFTM series lathes. Hard turning refers to machining hardened steel, typically between 58 and 68 HRC on the Rockwell scale, in a single-pass operation that replaces traditional grinding. The VDFT series lathes are purpose-built for this kind of work, featuring a rigid vibration-damping cast iron bed, high-precision spindle bearings, and CNC control systems that maintain dimensional tolerances within just a few microns. Using cubic boron nitride or ceramic cutting inserts, these machines can achieve surface finishes of raw 0.4 micrometers or better, results once thought impossible without grinding. Lead-free turning addresses a newer but equally important challenge. Traditionally, small amounts of lead were added to steel alloys to improve machinability. Modern environmental regulations have eliminated that option. The VDFTM machines meet this challenge head-on, combining optimized cutting geometry, advanced tool coatings like TIALN, and precisely controlled feed rates to achieve clean, burr-free cuts on lead-free steel. The result is cleaner metal, cleaner air, and parts built to last craftsmanship for the 21st century. Electric motors are everywhere in American industry, pumping water, running conveyor belts, driving compressors, and keeping HVAC systems humming. When one of these workhorses finally needs repair or reconditioning, you can't just grab a wrench and start pulling things apart. That's where specialized motor disassembly equipment comes in. The process begins with motor identification and documentation. Before anything is touched, technicians photograph every connection, record nameplate data, voltage, current, RPM, insulation class, frame size. This baseline data is critical for proper reassembly and for diagnosing what caused the failure in the first place. Next, the motor is secured in a purpose-built motor stand or fixture, which holds it safely and allows it to be rotated into the ideal working position. These stands are hydraulically adjustable and rated for loads far exceeding the motor's weight, providing a stable, safe working platform for every step that follows. Coupling and mounting hardware removal comes next. Hydraulic bearing pullers, rather than hammers and brute force, are used to carefully extract shaft couplings, pulleys, and fan assemblies. Using the right pulling force prevents shaft scoring and bearing seat damage that could compromise the repaired motor's performance. Then the end bells, the front and rear covers, are removed. On large motors, these can weigh hundreds of pounds, so overhead hoists and lifting fixtures sized to the specific motor frame are essential. The end bells are guided off carefully to avoid dragging them across the stator windings or rotor, which could cause additional damage. With the end bells off, the rotor can be extracted. This is perhaps the most delicate step. The rotor of a large motor sits in extremely tight clearance, sometimes just a few thousandths of an inch from the stator bore. Specialized rotor pulling fixtures distribute the lifting load evenly across the shaft to prevent bending, while technicians guide the rotor out slowly and steadily, watching for any contact with the stator windings. Once fully disassembled, every component bearings, windings, rotor, stator core, shaft is inspected, measured, and evaluated. Worn bearings are cataloged for replacement, winding insulation is tested with a megohummeter, shaft journals are checked for roundness and surface finish. It's meticulous, methodical work, and it's exactly that care that gives a rebuilt motor a second life, often running just as reliably as the day it left the factory.